Так, ну вроде должно бы уже... Сейчас посмотрим. Вот я просто... с большой задержкой просто. Да, вроде уже пошло. Пошло. Спасибо. Я просто какое-то время ждал, может, кто-нибудь из студентов придет. Но там уже 5 человек ждут трансляции, смотрят, так что... Нет, я просто на доске. Ну, может, еще придут. Okay, so let's begin. Well, our plan for the second half of our course is to discuss the basic theory of commutative Banach algebras, and then to apply it to the spectral theory of normal operators on the Hilbert space. And the subject of today's lecture is the maximal spectrum. The maximal spectrum and the Defund transform. For commutative Banach algebras. Well, from now on we adopt the following convention. The convention is that our base field is the field of complex numbers. So everything will be over the complex numbers. By an algebra, I always mean an associative algebra over the complex numbers. Associative algebra A. And we say that A is unital. A is unital if it has an identity element. Which will be denoted just by 1. If A is a unital algebra, then we can consider a set of all invertible elements. This set will be denoted by A cross. This is the set of all invertibles in A. The so-called multiplicative group of A. Okay, so from now on we assume that A is a commutative unital algebra. This is our basic assumption. So at this point, this is a pure algebraic object. We don't assume that A is a Banach algebra. At this point, this is just a commutative unital algebra. And we give the following definition. Suppose that we have a proper ideal, I of A. Proper in the sense that it is not the whole algebra. And we say that the proper ideal I of A is maximal. If it is not strictly contained in a bigger proper ideal. If there is no proper ideal J, such that I is contained in J. I is strictly smaller than J. So in other words, if we consider the partially ordered set of all proper ideals, it is ordered by inclusion, the maximal ideal is just maximal element of this partially ordered set. Here's another useful characterization of maximal ideals, a useful exercise for you. A proper ideal I of A is maximal even only if the quotient of A modulo I is a field. This is just an exercise in elementary algebra. And here's a basic example. An example and an exercise at the same time. Well, probably before I give this example, let's introduce some terminology. The set of all maximal ideals will be denoted like this. Max of A. This is the collection of all maximal ideals. And this set is called the maximal spectrum. The maximal spectrum of A. And here's a basic example, and an exercise at the same time. Let's look at the maximal spectrum of the polynomial algebra. The polynomial algebra in one variable. So I claim that there is a bijection between this set, the maximal spectrum of the polynomial algebra, and the complex plane. Bijection. And this bijection looks as follows. If P is a point on the complex plane, then the respective maximal ideal, let's denote it by MP, consists of all polynomials F which vanish at P. So this correspondence is a bijection between the complex plane and the maximal spectrum of the polynomial algebra. In fact, this result holds for polynomial algebras in several variables as well, but this is quite non-trivial. In fact, this is a weak form of Hilbert's Nullstellensatz. But for a single variable, this is absolutely elementary. How about the existence of maximal ideals in the general case? Well, it turns out that maximal ideals always exist. And moreover, we have the following proposition. Each proper ideal of A is contained in a maximal ideal. Is contained in a maximal ideal. The proof is a standard application of Zorn's lemma. So we take an ideal, the proper ideal I of A, and we consider the following set, let's denote it by M, which consists of all those proper ideals J of A, which contain I. So clearly this set is non-empty because it contains I itself. I claim that if we consider M as an ordered set, so the order is just the inclusion, then the set satisfies the conditions of Zorn's lemma. that is, each chain, each totally ordered subset of M has an upper bound. Why is it so? Well, indeed, let's take a chain. Let C be a chain M. A chain of ideals containing I. And to construct an upper bound, we just take the union of all ideals in C. Let K denote the union of C, the union of all ideals in C. So since C is a chain, it's more or less clear that K is an ideal. K is an ideal of A, and clearly it contains I, because each ideal in C contains I. Why is it proper? Why is it proper? We consider only proper ideals. It is proper because each ideal in C is proper. So if you take the identity of the algebra, and it's essential here that A is assumed to be unital, then the identity of A doesn't belong to any ideal in C. So for each J in C, the identity of A is not in J. And this implies that it is not in K. And so K is proper. So K is a proper ideal. It contains I, so it's an element of M. And clearly, by construction, K is an upper bound for C. So this implies that K belongs to M, and K is an upper bound for C. So each chain in M has an upper bound, and Song's lemma now shows that M has a maximal element. And this is exactly the maximal ideal we are looking for. Okay, let's now introduce another set, which is closely related to the maximal spectrum. This is the so-called character space. So let's recall the following algebraic definition. A character of A is an algebra homomorphism. An algebra homomorphism that is denoted by chi from A to the complex numbers. And let's also observe, so since our algebra A is assumed to be unital, let's observe that if chi is non-zero, then it automatically preserves the identity. It is unital. Well, indeed, if chi is non-zero, then it is surjective, because it is a linear functional. So a non-zero linear functional is surjective, and now it's elementary to show that you have a surjective homomorphism between unital algebras, then this homomorphism preserves the identity. It has this property. Okay, now we give the following definition. We define the character space. The character space of A is a set of all non-zero characters. And this will be denoted by A hat. set of all non-zero or equivalently unital characters. Okay, let's now observe that if you take any non-zero character of A, then its kernel is a maximal ideal. Its kernel is a maximal ideal. This is clear because it is an ideal, and it has codimension 1, because chi is linear functional, and clearly a codimension 1 ideal is maximal. So we have a map, we get a map from A hat to the maximal spectrum, which takes each character to its kernel. Let's now observe that this map is always injective. I have the following proposition. The map from A hat to the maximal spectrum, which takes each character to its kernel, is injective. Well, indeed, suppose we have two characters, say chi1 and chi2, and suppose that they have the same kernel. Well, they have the same kernel. This implies that they are proportional. Chi1 equals lambda chi2 for some lambda. Just because they are linear functionals. If two linear functionals have the same kernel, then they are proportional. So now we have to show that lambda is 1. And let's just evaluate this equality at the identity. So both chi1 and chi2 are unital. So we get the following equality, and this is lambda. So lambda equals 1, and therefore chi1 equals chi2. And that's it. So our map is injective. Well, now our initial question is it bijective? The answer depends on the algebra. Here are some examples and exercises at the same time. For example, if you take the polynomial algebra in one variable, C of t, then our map is bijective. And in fact, the same result holds for any finitely generated algebra. Again, this follows from Hilbert's Verstellen Satz. But this is absolutely elementary. This doesn't, for one variable, this doesn't require any form of the Verstellen Satz. But on the other hand, if we take some field containing the complex numbers, if A is a field strictly containing the complex numbers, well, for example, the field of rational functions in one variable, then the character space is empty. There are no characters of A. But the maximal spectrum is non-empty. The maximal spectrum consists of a single point, namely the zero ideal, which is maximal because A is already a field and there are no other maximal ideals of A. In any case, this, of course, this shows that our map is not a bijection in this case. Our next goal will be to show that this map is a bijection provided that A is a commutative unital Banach algebra. So from now on, we assume we assume that A is a commutative unital Banach algebra. We have a following useful lemma, which states that each maximal ideal of A is closed. Each maximal ideal of a commutative unital Banach algebra is closed in A. Well, let's take a maximal ideal. Let's take a maximal ideal I. And let's take the closure of I. It's a simple exercise to show that the closure of an ideal is also an ideal. This really follows from the continuity of the multiplication in A. So the closure of I is an ideal, and let's assume that I is not closed. Suppose that I is not closed, so the closure of I is strictly bigger than I, but I is maximal. I is maximal, and so this implies that the closure of I is equal to A. It is not a proper ideal, just by maximality. So, in other words, I is dense in A, and or equivalently, the intersection of I with any non-empty open set is non-empty. And therefore, if we consider the intersection of I with the multiplicative group with a set of all invertibles, it is non-empty. Because the set of all invertible elements in any unital Banach algebra is open. A cross is open. In A, this is the basic fact of Banach algebra theory, which was proved in the previous term. So I'm assuming you know this result. So this intersection is non-empty. In other words, I contains invertible elements. But if an ideal contains at least one invertible element, then it is equal to A. So I equals A, and this is a contradiction. And this contradiction completes the proof. So we have assumed that I is not closed, so it is closed. As a corollary, we see that our algebra, any commutative unital Banach algebra, doesn't have dense proper ideals. Because any proper ideal is contained in a maximal ideal, and the maximal ideal is always closed. So a proper ideal is never dense. This is maybe quite a little bit surprising, because if we consider just vector subspaces, then of course we can always find, if A is infinite dimensional, we can always find many codimension 1 non-closed subspaces. Just take any discontinuous linear functional. There are many discontinuous linear functionals on any infinite dimensional normed space. This is quite easy. And so the kernel of any such functional is a codimension 1, a dense codimension 1 subspace. So there are many dense codimension 1 subspaces. in any infinite dimensional normed space. But maximal ideals of a commutative unital Banach algebra are always closed. Okay, now by using this result, we can show that our map from maximals from the character space to the maximal spectrum is bijective. Theorem. If A is a commutative unital Banach algebra, then the map from A hat to the maximal spectrum, which takes each character to its kernel, is bijective. Well, we already know that it is injective, so now we have to show that it is surjective. Before we do it, let's make a little observation. Suppose that A is a Banach algebra, not necessarily unital, not necessarily commutative. And suppose that I is a closed two-sided ideal. Closed two-sided ideal way. Then the quotient of A modulo I is a Banach algebra in a natural way. This is a Banach algebra with respect to the quotient norm. So let's call that the quotient norm is just the following infimum. Well, indeed, it's an algebra because we quotient out a two-sided ideal. It's a Banach space because the quotient of a Banach space modulo a closed subspace is a Banach space. And it's elementary to see that this norm, the quotient norm, is submultiplicative. So the quotient of A modulo I is a Banach algebra. In fact, we have already used this observation some time ago when we defined the Kalpan algebra, which is the quotient of B of H of B of E, the algebra of bounded linear operators on the Banach space, modulo the ideal of compact operators. Okay, let's now apply this observation to the proof of this theorem. So we take a maximal ideal, I of A, and what we want to do is to show that I is actually the kernel of a character, which is necessarily unique. So let's consider the quotient of A modulo I, and let's observe that this is a Banach field. It's a Banach algebra because I is a closed ideal, and it's a field because I is maximal. So it's a Banach field. And now let's recall the Defund mother theorem, which states that any Banach field, or more generally any Banach division algebra, is actually complex numbers. So this algebra is isomorphic to the complex numbers. And now to complete the proof, we just look at the following picture. So we have the quotient map of A to A modulo I. This is isomorphic to the complex numbers. The composition of these two maps is clearly a character, chi, and by construction, I is equal to the kernel of chi. And this completes the proof. So we already know that this map is always injective, and now we have proved that it is actually bijective provided that A is a Banach algebra, a commutative unital Banach algebra. Okay, well, here's a useful corollary, which gives us a nice invertibility criterion for an element in our algebra. So I claim that an element A in our algebra A is invertible, even if each character of A doesn't vanish at this element. Well, the left-to-right implication is obvious. This is clear because, well, a non-zero character is a unital algebra homomorphism, and unital homomorphism takes invertible elements to invertible elements. And to prove the right to left implication, suppose that A is not invertible. Suppose that A is not invertible. In this case, the principal ideal generated by this element is proper. The principal ideal generated by A is proper. And the proper ideal is contained in maximal ideal. There is a maximal ideal I of A such that this principal ideal is contained in I. But we already know that I is the kernel of a character. I is the kernel of some character chi. And so this implies that chi vanishes at little a. And this completes the proof. Okay. Well, so far, the maximal spectrum is just a set. Our next goal will be to make it into a topological space. Towards this goal, we adopt the following convention. So from now on, let's identify the maximal spectrum and A hat by means of this canonical projection. This is quite convenient because in some situations it is more convenient to think of the elements of the set as maximal ideals, but in in other situations it would be more convenient to look at them as characters. Okay, let's now recall the following basic fact from Banach algebra theory, which states that all characters of A, all characters of a unital Banach algebra, are continuous, and moreover they are contained in the closed unit bowl of the dual space. The set of all their functionals of norm less than or equal to 1. The closed unit bowl of the dual space. So this is a basic fact of Banach algebra theory. In fact, this is true for any unit of Banach algebra, not necessarily commutative. And now we get the following definition. We define the Defund topology. The Defund topology on the maximal spectrum of A, which is identified with A hat, with the character space. We define it to be the restriction of the weak star topology. It's the restriction of the weak star topology to the character space. So there's the weak star topology is defined on the dual space. We take the restriction to A hat, and what we get is the Defund topology on the spectrum. So the maximal spectrum becomes a topological space. I claim that the space is compact and Hausdorff. Maximal spectrum of A is compact and Hausdorff. Well, first of all, it's clearly Hausdorff because the weak star topology on A star is Hausdorff. A star equipped with the weak star topology is Hausdorff. And so is A hat. Why is it compact? Let's recall from the previous lecture, let's recall the Banach-Alou-Bourbaki theorem, which implied that the closed unit ball is compact for the weak star topology. The unit ball of A star is compact for the weak star topology. And the hat is contained in this ball. So to complete the proof, we have to show that a hat is closed in the unit ball. I have to show that a hat is closed in the unit ball with respect to the weak star topology. And to show that it is closed, let's observe the following. So we take any two elements, little a and little b, in our algebra, and let's observe that the following map, the map from A star to the complex numbers, which takes f to f of AB minus f of A f of B, this map is continuous. And actually we need another map which takes f to, well, this is just the evaluation map at the identity. So these two maps defined on a star, they are continuous for the weak star topology. Well, this is clear because this is just the evaluation map, which is obviously continuous. The product of two evaluation maps is continuous because each of them is continuous, and the difference of two continuous maps is continuous. So they are continuous. But on the other hand, the character space, A hat, is nothing but the set of those f for which this is identically 0 and this is 0. F of AB minus f of A f of B is 0, and f of 1 equals 1 for each A and B. So these two conditions determine A hat. This condition means that f is an algebra homomorphism, and this means that f is unital. But now, since these two maps are continuous, it's immediate from this equality that A hat is closed. implies that A hat is a closed subset of the ball. So it is compact. And it is closed because, well, this is for each fixed pair A and B. This is closed because this is the preimage of a point under a continuous map. And now we just take the intersection over all pairs A and B, and we get this. And the intersection of any family of closed sets is closed. Okay, so the maximal spectrum is a compact Hausdorff topological space for the Defund topology. And now we are ready to introduce one of the main concepts of the theory of commutative Banach algebras, namely the Defund transform. First we define the Defund transform of an element in A. The Defund transform of an element on level A in our algebra is a function, A hat, a complex valued function A hat on the maximal spectrum which is given by the following simple formula. So if little x is a character, so we identify the maximal spectrum with a character space. So if chi is a character, then A hat evaluated at x is just x evaluated at A. So a very simple definition. Well, so we get a function on the maximal spectrum. I claim that this function is continuous. Proposition A hat is continuous. To show that it is continuous, we observe that this formula implies that A hat is nothing but the restriction of the canonical image of A in the bidual. So A hat is I way. So I way is an image of A under the canonical embedding. It's a linear functional on A star. And we just restrict it to A hat. So where I is the canonical embedding of A into the bidual. And let's now recall from probably this was the previous lecture, that the image of this canonical embedding consists exactly of those linear functionals on a star, which are weakly star continuous. The image of I consists exactly of weakly star continuous linear functionals on a star. So this element is a weakly star continuous linear functional, and after we restrict it to A hat, we get a function continuous for the Defund topology. And that's it. Okay. So thus we see that for any element little a in our algebra, we have constructed a continuous function on a maximal spectrum. So we get a map from A to the algebra of continuous functions on the maximal spectrum. And this map is called the Defund transform of our algebra. the Defund transform of A is map gamma A, from A to the algebra of continuous functions on the maximal spectrum, which takes each element real A to the function A hat. Let's now look at some basic properties of the Defund transform. So we have the following theorem. First of all, the Defund transform is a unital algebra homomorphism. Unital algebra homomorphism. Second, it is bounded, and moreover, the norm of gamma is 1. Next property, property 3. For each element A in A, the supremum norm of the Defund transform of A hat is nothing but the spectral radius of A. The spectral radius of A. Property 4, for each element A in our algebra, the spectrum of this element is equal to the range of the function A hat. And finally, property 5, the kernel of the Defund transform, so by construction this is the closed ideal, because it's a kernel of continuous unital homomorphism. So this is the intersection of all maximal ideals. The intersection of all maximal ideals of A. Or currently, this is the set of all quasi-nilpotent elements in A. The set of all quasi-nilpotent elements of our algebra. Just in case, let's recall that an element of Banach algebra is called quasi-nilpotent. The way is quasi-nilpotent if its spectrum is 0. Or currently if the spectral radius is 0. And by the Berling-Defund formula, this means that the following limit is 0. So maybe even more explicitly, this means that the norms of the powers of A decay faster than any geometric progression. This explains the terminology. This explains why such elements are called quasi-nilpotent. If A is nilpotent, then this condition is clearly satisfied. But on the other hand, there are some natural examples of quasi-nilpotent operators. For example, the Volterra operator on the little O2 space, which are quasi-nilpotent but which are not nilpotent. Okay, let's now prove this result, proof of theorem. Well, part 1 is clear. This is a little exercise for you, just more or less immediate from the construction. Let's now prove part 4. This will be more convenient to prove part 4. Let's look here. So the right-hand side of this equality, the range of a hat, is nothing but the spectrum of a hat considered as an element of the algebra of continuous functions. So the right-hand side of this equality is nothing but the spectrum of a hat in the algebra of continuous functions. So this equality means that the Defund transform preserves the spectrum. So we already know that it's unital homomorphism. And property 4 means precisely that this homomorphism is spectrum preserving. But it's an elementary fact, which was already discussed in the previous term, that unital algebra homomorphism preserves the spectrum even only if it takes non-invertibles to non-invertibles. So to prove 4, we now have to show that gamma takes non-invertibles to non-invertibles. This inclusion is equivalent to the fact that gamma preserves the spectrum. Okay, let's take a non-invertible element in our algebra. We already know that an element is non-invertible if and only if some character vanishes at A. There is a character, x, such that x vanishes at A. This was proved 15 minutes ago. But this means actually that a hat vanishes at x. We will find transform, a hat vanishes at x. So a hat is not invertible. In the algebra of continuous functions. And this completes the proof of part 4. So we have proved that gamma takes non-invertibles to non-invertibles, and this is equivalent to property 4. Now let's observe that 3 is immediate from 4. Well, indeed, if we take the supremum here and here, the supremum of the absolute values of points in this set, then this is the spectral radius. And the supremum of the absolute values of points in this set is nothing but the supremum norm of a hat. And we get this equality. Property 2 is now a special case of 3, because we know that the spectral radius of any element in any unit Laban algebra is less than or equal to the norm. This inequality holds in any unit Laban algebra. And so gamma, the norm of gamma is less than or equal to 1. But since it is unital, and since the norm of the identity element is equal to 1, we conclude that the norm of gamma is 1. Finally, let's look at the kernel of the Defund transform. So by construction, the kernel of the Defund transform so it consists of all A for which A hat is identically 0, and A hat is identically 0 if and only if all characters vanish at A. So this is the intersection of the kernels of all characters. But we already know that the kernels of characters are nothing but maximal ideals. So we get this. And finally, if we look again at property 4, we see that the kernel of gamma is nothing but the set of all quasi-nilpotents. So alpha is in the kernel if and only if this is 0. The spectral radius is 0, which means that A is quasi-nilpotent. And this completes the proof. By the way, there is a special name for the intersection of all maximal ideals, which appears in this formula. And this definition makes sense for any commutative ring, actually, or for any commutative algebra. I remark. If A is any commutative unital algebra, then the intersection of all maximal ideals is called the Jacobson radical. The Jacobson radical of A is just the intersection, J of A is the intersection of all maximal ideals. And let's say that A is Jacobson semi-simple if this is 0. Okay, the Jacobson radical is 0. By the way, it's useful to compare this. So for those of you who are familiar with commutative algebra, it's useful to compare this with the nil radical, which is defined to be the intersection of all prime ideals. And which is of course bigger because any maximal ideal is prime. And so the Jacobson radical is in general bigger than the nil radical. And it's known that the nil radical consists of all nilpotent elements. While the Jacobson radical is provided that A is a Banach algebra, the Jacobson radical consists of all quasi-nilpotent elements. So in the general case, the Jacobson radical can be bigger than the nil radical. Okay. Let's now look at some concrete cases. So our next goal is to describe explicitly the maximal spectrum and the Defund transform for the algebra of continuous functions on a compact Hausdorff topological space and for some subalgebras of this algebra. Examples. Defund transform for some subalgebras of COX. In particular, we will see that for any compact Hausdorff topological space X, the maximal spectrum of COX is naturally identified with X, and after this identification, the Defund transform becomes just the identity map. Okay, so suppose that X is a compact Hausdorff topological space. And for each point X in our space, let epsilon X denote the evaluation character of COX. This is just the evaluation at little x. So clearly this is a character of our algebra. And let's denote by nx its kernel. This is the ideal of functions vanishing at x. We have the following lemma. I claim that for each proper ideal, I in COX, there is a point, little x, in our space such that I is contained in nx. So there is a common zero for all functions in our ideal. In some sense, this lemma can be interpreted as a weak form of Nullstellen Satz for the algebra COX. But of course, the proof is much simpler than the classical Nullstellen Satz for polynomial algebras, because of some special properties of our algebra, of the algebra of continuous functions. So to prove this result, let's assume that this is not the case. So let's suppose that for each point in our space, there is a function fx in our ideal, such that fx doesn't vanish at x. So we want to deduce a contradiction from this. Well, fx is a continuous function. It doesn't vanish at x. So by continuity, it doesn't vanish on a suitable neighborhood of x. There is a neighborhood ux of x such that fx doesn't vanish on this neighborhood. This is non-zero for any y in ux. So we can construct such a neighborhood for any point in our space. So we get an open cover of x, and by compactness we can find a finite subcover. By compactness, x can be represented as a finite union uxi from 1 to n. And let's now consider the following function, f, which is given by the following formula. Or equivalently, we can write this in the following form. Fxi complex conjugate fxi. So what can I say about this function? On the one hand, it belongs to I, because fxi sits in I, and I is an ideal. So because of this equality, we see that f is an element of our ideal. And since each summand is non-zero, more exactly strictly positive on the respective open set in this union, we conclude that f is strictly positive everywhere. F of y is strictly positive for each y in x. So it is invertible. F is invertible in COX. So we see that our ideal I contains an invertible element. But this can happen only if I is the whole algebra, which is a contradiction, because I was assumed to be a proper ideal. So this contradiction completes the proof. It shows that for each proper ideal, there is a common zero in X. As a corollary, we see that the map from X to the maximal spectrum of A, which takes X to Mx, or equally we can look at this map as a map from X to a hat, which takes X to epsilon X. Here we use our convention that we identify the maximal spectrum with the character space. So this map is bijective. And here, of course, A, what is A? A is C of X, the algebra of continuous functions on X. Let's write this explicitly, C of X. So this map is bijective. Well, indeed, it is, first of all, it is injective, because continuous functions separate the points by Rousseau's lemma. So if we have two distinct points, x and y, then epsilon x is not equal to epsilon y. So this map is injective by Rousseau's lemma, and this lemma shows that it is surjective. Each maximal ideal is of this form. In fact, we will see in a couple of minutes that this map is a homomorphism. But before we can do it, let's look at the following simple construction. Suppose that X and Y are compact Hausdorff topological spaces. And suppose that F is a continuous map from X to Y. Then we can consider the induced map, let's denote it by F dot, from C of Y to C of X, given by the following formula. If phi is a continuous function on Y, we can just consider the composition of phi and F, and this will be a continuous function on X. And let's observe first of all that F dot is a unital algebra homomorphism. F dot is a unital algebra homomorphism. Moreover, F dot is continuous, it is bounded, and the norm of the F dot is 1. Well, indeed, the supremum of this function over y is clearly less than or equal to the supremum of phi. Sorry, the supremum of this function over x is clearly less than or equal than the supremum of phi over y. So the norm of this is less than or equal to the norm of phi, and so the norm of F dot is less than or equal to 1. But since it is unital, its norm is exactly 1. Property 3 is absolutely trivial. if we take the identity map of X, then the norm of the induced homomorphism is just the identity map of C of X. And finally, property 4, if we have two continuous maps, say F and G, F from X to Y, and G from Y to Z, then we can consider the composition, and the induced homomorphism, GF dot, is equal to F dot G dot, just by construction. So in fact, all these properties imply that what we've just constructed is a contravariant functor from the category of compact topological spaces, of compact Hausdorff topological spaces, to the category of commutative unital Banach algebras. We'll discuss this functor in more detail a bit later. And at this point, what is important for us is that these four conditions imply that, so in particular, they imply that if F is a homomorphism, if F is a homomorphism, then F dot is an isometric isomorphism. F dot is an isometric isomorphism. Well, indeed, if F is a homomorphism, then F dot is an algebra isomorphism because of properties 3 and 4. If G is inverse to F, then G dot is inverse to F dot. And it is isometric because, well, F dot is contractive. It doesn't increase the norm. And the same is true for the inverse. But a linear map between normed spaces is an isometry, if and only if this map is bijective and both this map and the inverse map are contractions. So this means that F dot is an isometric isomorphism. We now have the following theorem, which applies to many concrete examples of commutative Banach algebras. So suppose that X is a compact Hausdorff topological space. And suppose that A is a subalgebra in C of X, which contains the function which is identically 1. The function which is identically 1 belongs to A. And suppose that A satisfies the following conditions. Condition 1 is that A is a Banach algebra. A Banach algebra with respect to a norm that dominates the supremum norm. So in particular, this applies in the case where A is just a closed subalgebra in C of X. In this case, it's a Banach algebra under the supremum norm. But on the other hand, there are many situations for which A is a Banach algebra under a stronger norm. For example, we can consider the algebra of continuously differentiable functions, C1 functions, on the closed interval of the real line. And it's a Banach algebra under its own norm, which is strictly bigger than the supremum norm. So this is condition 1. Condition 2, A separates the points. A separates the points of X, which is also quite a natural condition. And finally, condition 3, for each maximal ideal I of A, there is a point x in X such that I equals mx. Or equivalently, for each character I of A, there is a point such that chi equals epsilon x. I claim that if these conditions are satisfied, then the map epsilon from x to a hat, which takes x to epsilon x, is a homomorphism. Between x and the character space, or equivalently between x and the maximal spectrum of A. And moreover, the following diagram commutes. And here's the diagram. This is A. This is C of x. So we have the inclusion map here. Just the inclusion map, because A is a subalgebra in C of x. We can also consider the algebras of continuous functions on the maximal spectrum. And the Defund transform, which acts from A to this algebra. And finally, since epsilon is a homomorphism between x and the maximal spectrum, we have the induced map here, epsilon dot, which is an isometric isomorphism. An isometric isomorphism because of this observation. And this diagram commutes. So this means that up to this identification, the Defund transform of A becomes the inclusion map of A into C of x. Before we prove this theorem, let's, I recommend you to do the following simple exercise, which is more or less automatic, but is useful. Suppose that X is any topological space, any topological space, and E is any topological vector space. And suppose we have a map phi from X to the dual of E equipped with a weak star topology. I claim that this map is continuous, even only if for each element V in E, the map, the function that's denoted by phi V from X to the complex numbers, which takes x to phi of x evaluated at V, is continuous. This is a simple exercise which is almost immediate from the definition of the weak star topology. Actually, the weak star topology is the weakest topology on E star for which all evaluation maps are continuous. So this almost immediately implies that a map from here to here is continuous, if only if all such compositions with the evaluation maps are continuous. Okay, and finally, maybe let me finish the proof of the theorem because it is quite short. I hope 3 minutes will be enough. Proof of theorem. First of all, if we look at conditions 2 and 3, we see that they together imply that this map epsilon is bijective. Conditions 2 and 3 together imply that epsilon is bijective. This means the injectivity. Condition 2 is the injectivity of epsilon, and condition 3 is the surjectivity. Okay, why is it continuous? To show that epsilon is continuous, we apply this exercise. So epsilon is continuous if and only if, for each A in A, the map which takes x to epsilon of x evaluated at A is continuous. But epsilon of x evaluated at A is just A of x. And A is assumed to be continuous. This is just A of x. So we see that epsilon is continuous. Well, epsilon is continuous, and it acts between compact Hausdorff topological spaces. And it's a simple fact from elementary topology that a continuous bijection between compact Hausdorff spaces is a homeomorphism. So these spaces are compact and Hausdorff. And so epsilon is a homeomorphism. And finally, we have to show that the diagram commutes. And this is just an explicit computation. So if we compose these two arrows, epsilon dot and gamma, so we apply it to an element little a, and let's evaluate it at, say, little x. We want to show that this is just A of x. By the definition of epsilon dot, this is gamma of A evaluated at epsilon x. By the definition of epsilon dot, this is gamma of A evaluated at epsilon x. But now by the definition of gamma, this is epsilon x evaluated at A. But epsilon x evaluated at A is just A of x. And so we conclude that the diagram commutes. Okay, and this completes the proof. So we see that for many natural subalgebras in C of x satisfying some reasonable conditions, the Defund transform becomes just the inclusion map into C of x. In particular, for the case where A is just C of x, we get the following corollary. If A is C of x, where x is a compact Hausdorff topological space, then gamma A is an isometric isomorphism. An isometric isomorphism. And the inverse map is just epsilon dot. Because in this case, this arrow is just the equality. So we see that epsilon dot composed with gamma is the identity map. And since epsilon dot is an isometric isomorphism, we conclude that gamma is also an isometric isomorphism. Okay, so that's all for today. In the next lecture, we introduce a very important class of algebras, the so-called C-star algebras. We discuss some basic properties of C-star algebras. And we will prove the fundamental result, the so-called Defund theorem, which states that for any commutative unital sister algebra, the Defund transform is an asymmetric star isomorphism. Здравствуйте. Так, сейчас надо остановить. Так, остановить.